if we go about results, first thing, the smoke. We want to look at the smoke. And that gave a headache because we ran the model for 7 days. We have hourly data, and it is hard to fit everything. So we went for the daytime average from 7 a.m. to 9 p.m., 14 hourly average. And if you look at the plot, the evolution of the plot, this is a 21 ensemble member average and 14 hours average. And if you look at the evolution of the smoke, the fire is increasing its area every day, and it is following the prevailing wind. And the wind barb is 850 hectopascal winds. So if we look at the smoke, what we expect, the radiation effect. So the shortwave, incoming shortwave radiation is the same plot, 21 ensemble member averaged and 14-hour averaged. And here we can see the significant differences in 14-hour average, the total daytime average. And here we found 367 watt per square meter at day 5 at 11 a.m. So we can see a bigger picture in hourly analysis, but when we average a couple of hours, we lose a lot of scenarios. So if we see the short wave is blocking, why it's blocking? Because the aerosol does the scattering thing, and that's why the less radiation reaching to the Earth's surface. As a result, the 2-meter air temperature, we have seen the significant differences in day 4 and day 5, plot D and plot E there. But it is hard to see the differences, especially in temperature, in a 14-hourly average. But if I don't have the plots, but I have the numbers. We have the maximum decrease, which we call surface cooling. So we got up to 2.8 degrees Celsius surface cooling due to forest fire smoke at day 3 and 2.7 at day 4. After that, the fire was getting a bit weak, so we are losing the temperatures. And of course, there will be changes in planetary boundary layer height because there are imbalance in the shortwave radiations. And we have seen the same pattern where we saw the smoke, we saw the surface dimming, which is incoming shortwave radiation, and also the surface cooling, which is 2-meter air temperature, and the planetary boundary layer. So every pattern matches together. But if hourly, we ended up to finding 972-meter decrease in planetary boundary layer height at day 4. And we also did the analysis on 10-meter wind speed. I'm not showing the plots. Then out of curiosity, I wanted to see how high the smoke, the plume is going, because WRF-Chem is famous for underestimation of the plume rise. So the top 2 panel is the HF, Highland Fire. I just made a cross section to see how far it goes. There is nothing going beyond 3 kilometers. And for the down 2 rows, these are the ground fire, same case, not reaching up that, because we know there is a saying in the world that fire creates its own weather. And to have that, we have to have the emission on like upper troposphere or stratospheric level so that we can see the thing. And on the right side, it's a nighttime. For our work, we didn't include the nighttime analysis because we were dealing with shortwave. So in nighttime, we don't have any incoming shortwave. Sorry. So here, this is the old plot. You guys already have seen the plot, but on the top left, plot A, we choose 3 locations, RL and Moses Lake, ML, and the Leavenworth, LV, to see on the location plot, and we made a temperature profile. And in our temperature profile, we have seen that, okay, we have seen the surface cooling, but a mid-tropospheric warming. And in our case, the maximum we found, 0.6 degrees Celsius in mid-tropospheric warming. And our second objective was to see the synoptic scale. If it is, so far we have seen the local scale, but when I plotted to see the synoptic scale, I didn't find anything significant. So we concluded that a 7-day lasting cluster of fire is not contributing to a regional scale or far afield. So the discussion is, okay, smoke caused surface cooling up to 2.8 degrees Celsius and mid-tropospheric warming of 0.6 degrees Celsius due to aerosol radiation interaction. And we have the shortwave radiation reduced up to 335 watt per square meter, altering the surface energy balance. And we have seen the decrease in planetary boundary layer height, which is 916 is the average, but the highest we got is 978. And we have also seen the 1.9 meter per second decrease in 10 meter wind speed, which I haven't shown it here. And the plume heights were low. So this is the first study apart from the developers that we are using this model. So we gave them feedback that this is the thing we're happening. The plume heights is not reaching up to the mark so that we can see the pyro activities or something else. And another plan to add this, we're adding a 1 kilometer resolution, because my resolution is 4 kilometer resolution. There you cannot see the pyro activities really well. So we have to downsize the resolution. We're adding some more simulation, and it's already under review. So thank you.
Thank you very much. So we have lots of time for questions. Can you ask, and could you repeat the question? Answered.
So the reason of mid-tropospheric warming, if you go near to a fire, what you see, what you feel, the heat. We can feel the heat at the side, but the heat is the updraft going to the atmosphere. And the atmosphere should balance. So if you have a surface cooling at the base, at the surface, you are expecting a mid-layer warming on the, like, it depends on the height. It depends on the location. Yeah. But the heat transport happens because the upper of the smoke is blocking the sun way. What is happening over the smoke? The what's called the heat transport.
We have other questions. Are there any questions from online? No, there aren't. Okay. Well, I'll just ask one more question. And this is to all speakers. People could remember to repeat the question. In terms of the aerosol radiation interaction, does the WRF simulation include black carbon aerosol, and what role would that play?
Black carbon aerosol they include, but the black carbon aerosol is mainly the absorbent. They absorb the heat. But in our work, we wanted to see the scattering option. So the black carbon BC, they don't scatter, they absorb.
No, exactly. But is it playing an important role in the energy budget?
Of course.
Okay. All right. Any last questions? We have time for one more. If not, let's thank our speaker once again.
Thank you.
Okay, and now we are going to attempt, and hopefully this works. We have had a presenter who's unable to attend in person, but has sent a video. So we will play this, and I think we've got the audio set up, so I think we're good to go. And let's start here.
Dear distinguished experts, due to unforeseen circumstances preventing our physical attendance at this result presentation, we sincerely apologize. My name is He Qing, and I will be delivering this presentation via pre-recorded video. The title is Layering of Dust Aerosols and Interaction with the Atmospheric Boundary Layer over the Taklamakan Desert in northwestern China. New insight from ground-based observations. As shown in Figure 1, our study focused on the Tarim Basin in Xinjiang, China. This region experienced frequent dust events with an annual average of more than 157 days of floating dust and approximately 16 days of dust storms. First, we conducted a series of investigations into the interactions between dust aerosols and the ultra-deep atmospheric boundary layer in the Tarim Basin. We performed the first vertical sounding observations of dust aerosols in this region, capturing their vertical atmospheric structure. From Figure 3, during daytime storm convective development elevates the convective boundary layer to altitude of 4,000 and 5,000 m. At night, a stable boundary layer forms at 160 m, overlaying a deep residual layer. During daytime conditions with heavy dust, the convective boundary layer top reaches 1,180 m at 1 p.m., significantly lower than on light dust days. At night, the stable boundary layer forms at 280 m, higher than on light dust days. A capping invariant layer approximately 1 kilometer thick develops between the convective boundary layer and the residual layer, functioning as a dynamic then dynamic barrier. This layer supplies vertical development of the convective boundary layer and impedes dust aerosols transport. From Figure 4 results, low-level dust transport occurs with a low-level jet, while high concentration dust aerosols persist in the residual layer, creating a vertically stratified dust aerosol suspension structure. Using the STAR model, we conducted simulation analysis to examine dust aerosols' vertical distribution impacts on atmospheric radiative heating rates under dust-no-dust conditions. Daytime dust aerosols radiative warming induce significant temperature inversion, forming an outer sea capping invariant layer. Nighttime dust aerosol radiation cooling formation of a thicker stable boundary layer. This cooling effect enhances or reduces stability above below the dust layer within the residual layer. This stability difference drive vertical dust aerosol mixing. Using two ground-based lidar deployed at the southern margin of the Tarim Basin, we analyzed the dust event process. Validation through compression of lidar extinction coefficient with capsule satellite data under clear sky and floating dust conditions showing strong consistency, confirming both method effectively characterize atmospheric pollution levels. Aerosol ECCC becomes significant event during intention dust interaction. Short-term dust storm surface level mixing of dust with pollution particles. Post-storm last dust particles undergo gravation, setting where small particles remain suspended at higher altitude. Calypso observations figure 10 confirm substantial dust aerosols persist below 4,000 m altitude. From Figure 11 and 12, during short-term dust storm at both sides, dust aerosols stratification with 1 km is particularly pronounced, with stable dust aerosol layer observed near 3 km altitude. Finally, our Wolfram model retrospection indicates this dust event was strongly influenced by effects, post-events. Suspended dust persists in the atmosphere at 4 kilometers altitude, forming durable suspended dust layers resistant to dispersion. Thank you for your attention. This slide background features a renewed quote from the Taklamakan Desert hinterland, which we share with you. There are only desolate deserts, but no desolate lives. Thanks again.
Well, thanks. Obviously, questions are not going to be an option, but I think there's an opportunity for a brief discussion if people are interested. Otherwise, I'm going to suggest we wait 5 minutes to start the next talk so we stay on time. So I'm happy to open the floor to discussion, or people can just ruminate on the talk silently. All right. In the absence of any burning points to discuss, why don't we get going again at 11 o'clock with our next presentation, which is going to be virtual. And do we have Bill online? Pardon? Well, let's see if he's online. Can you just do a quick test to see if he's... William, can we do a test of your audio?
Yeah, can you hear me?
Yeah, very well.
Not well?
Yeah. So then...
Can you hear me?
Yes, we can hear you. Can you hear us?
Yes, I can.
All right.
I could share my screen anytime.
We'll go ahead and share your screen.
I do.
But I think because people will be coming in at 11, why don't we hold off to starting the formal presentation until then?
Okay.
Screen. Let's just see if things are working. Well, we do whatever needs to get done. What do I need to do?
I sent a message to him.
Okay. Hi, William, can you try sharing your screen again?
Transfer to my screen. Okay. Let's see. How do I do this? I press the share screen button, but all I get is a choose what to share with. I don't get my screen. Can you?
Yes, we're just working on that, William.
Yeah, I just get a tab that says choose what to share with Studio restream.io, but I can't press the share button in that.
Yeah, we're just following up on that, William, to figure out what to do. What's going on? Oh, do we have to? We have to show them?
Yeah.
Okay. Okay, so I think, William, the way things are going to work is that we will be displaying your slides, and so you'll need to tell us when to update them.
Okay. I assume you're putting them up now?
Are they being shown? Can you see them, William?
Hello?
Are you able?
Are you able to see the slides?
No, I can't see the slides. Now I
You have them now? You have them now, William? And so you can see them now, William? Or did we lose? Sorry, everyone. We're just trying to navigate this brave new world of hybrid conferences.
You have to.
After what? I keep no training on this, so I have no idea.
No, you're.
Are you there, William? We have an organizer. There's no William. So we've lost the audio somehow with our presenter.
He's online, and we just can't hear him.
Is he able to hear us? Is he able to hear us? Hi, William. Are you there? Are you able to hear us? If you.
Can you hear me? Okay, can you go to the next slide? Can you go to the next slide? Can you go to the next slide? Excellent. So the common perception is that lighting will increase as lightning warms, but the picture over Canada is more nuanced than that. The detection efficiency of cloud-to-ground lightning hasn't changed much, so it's possible to analyze trends. We analyze Canadian Lightning Detection Network annual total lightning strokes. Uh, the results are very similar for flashes as well. We did total lightnings, that's CG, negative polarity, and positive polarity in 4 telescoping aerial resolutions, all of Canada and provinces, 7 CONUS regions, latitude strips in each province, and 50 kilometer by 50 kilometer equal area rectangles. And we applied a Mann-Kendall test at 95% confidence to detect trends. Next slide. On the left, you see the Canadian Lightning Detection Network sensor locations. On the top is for all of Canada, the black is total lightning, the blue is negative polarity, and the red is positive polarity. And what you see there's been a downtrend over the years since 1999. And on the bottom, I included the cloud-to-ground flashes, which go to 2024, and you see that 2024 dropped again from what it was in 2023. Next slide. There's a lot to see here. This is for every province. Essentially, in the north and the far west, we have an uptrend of total lightning. But in the east, particularly in the Great Lakes to Atlantic Canada, we have a downtrend of total lightning. So cloud-to-ground lightning is decreasing in that area. The red curve is positive, and you see positive lightning has been increasing steadily over the years. Next slide. This is the top two are the Great Lakes area for the US, the CONUS, and you see that the downtrend has continued across from Ontario and Quebec down into that area. And then when you get to the Great Plains on the bottom, you see that lightning had been increasing and then it began to decrease somewhere around 2009 approximately. On the right side, you see 3-degree latitude strips. We did analyze for all of the areas. Not too much change except for in British Columbia, where we saw in the south, lightning began to decline after 2009, but at approximately 52 north, the trend continued upward after 2009. Next slide. This is in the 2,500 kilometer squared equal area rectangles. And what you see is the red is uptrend, the down is blue, and the gray is no trend. And in the far west and in the north, you see an uptrend of total lightning. Negative lightning is very similar to total lightning, so I won't talk any more about that. But in the bottom, you see a vast area across Canada where positive lightning has been increasing steadily. And there's a diffuse boundary approximately of 52 in the north, or in the west, down to about 49 or so in the east. And that trend doesn't continue continuously across. So we think that this uptrend in positive lightning is not due to improvements in sensor detection. Next slide. Here's the decrease from 2014 to 2023, minus 2004 to 2013, and you see total lightning especially decreasing in the Great Lakes and Midwest area. But on the bottom, you see positive lightning has been increasing, particularly in northern Alberta and the territories and across the central prairies. Next slide. Mean current hasn't changed too much, except in the far west and the north, current above 75 kiloamps. Those strokes have been changing and increasing in strength. And positive lightning tends to have stronger currents, so it causes more damage at the ground and more potential for wildfires. Next slide. Factors contributing to these observed trends, the amplification of the Rocky Mountain Barrier wave, we feel has contributed to the downtrend east of the Rockies. And the northward reorganization of the summer mean polar front has contributed to the uptrend in the north, where synoptic scale systems are now traveling farther north than they were before. And the positive lightning, we feel one factor contributing is ingestion of wildfire smoke by convective cells. And all this occurs in the background of climate warming. Next slide. Here you see the 500 millibar geopotential heights for the 2004-2013 on the right and 2014 to 2023 on the left. And you see the amplification of that wave has occurred at that time. And if you take the difference between those 2 decades, you see that there's been an increase of heights as well as thickness on the bottom 2 slides across southern and central Canada, with a increasing baroclinic zone in the north. So we feel that this is reflective of a reorganization of the polar front towards the north. Next slide. This is at 300 millibars. First 2 slides are the meridional wind components, and the second 2 slides on the top are the scalar wind components at 300 millibars. The difference is the main thing to get here. What you see is declining on the bottom 2 there, declining wind speeds across the south, but increasing across the north. So again, this we think is reflective of the amplification of that Rocky Mountain Barrier wave towards the north, as well as the reorganization of the polar front. Next slide. And you see over the west there and in the north, this is vertical motion at 500 millibars. There's been increasing ascent in the west, but across southern central Canada, right to the Atlantic, you see a large area of sinking motion, which is, you see downstream of the ridge from that amplifying wave, the Rocky Mountain wave. And so you see this has continued through both decades, so it's been a long-term effect. On the bottom left, you see CAPE has been decreasing across southern prairies and into the Great Lakes, with small increases in the far west and north. And you see that a 2-meter relative humidity difference has been decreasing over a large area, particularly through the southern prairies and into the Great Lakes. And in the north there, along the Arctic coast, also decreasing there, which we feel is due to intrusion of continental drier air as synoptic scale systems move farther north. Next slide. This is the sea surface temperature has been warming in the eastern Pacific. You see, this is the difference between 2014 and 2023 and 2004 and 13. So there's been a significant increase, and so there's been increased advection of warmer air onto the continent from that. And we feel this is due to the positive phase of the Pacific decadal oscillation, which began in 2013. And in the positive phase, you get stronger ENSO events. There were 2 during this period after 2013, and also background climate warming. Next slide. And just to tie things together, you see on the top there, increasing cloud-to-ground lightning in northern BC and across northern Canada, and that's related to the, we feel, ascent ahead of the trough of the Rocky Mountain Barrier wave. And to the east of the ridge, you see declining lightning due to the large-scale mean subsidence occurring there. Next slide. Yeah, there you go. And you see that the ascending areas match with the increasing lightning pretty well, and the declining lightning across central Canada and the Atlantic matches pretty well with subsidence occurring there, as well as reduced CAPE and drier conditions. Next slide. And a factor contributing to the upward trend of positive lightning, we feel, is wildfire smoke ingestion in convective clouds. Here's a case from 15th May 2023, and you see that the smoke extends for a large area far downwind from the fires. On the right there, you see that the areas burned by wildfires, and that has increased significantly in the last decade. And also, as an aside, less convection occurs under smoky skies, as we saw in the first talk. So another contributing reason for cloud-to-ground downtrend east of the Rockies. And next slide. And just to summarize the conclusions here, on the national scale, the lightning is downtrending, but it's dominated by larger amounts of lightning in the Great Lakes area in the east compared to the west. An uptrend in northern BC and Alberta, Yukon, Northwest Territories. This is occurring over the boreal forest area with increased likelihood of wildfires. The trend accelerated after 2013. GCM studies predict increased lightning in northern latitudes as climate warms, and this, we feel, it's already underway. And downtrend to the east of the Rockies over a large area of Canada and USA, east of 95 west to the east coast. began in about 2005, reached Manitoba in 2016, and southern Alberta and Saskatchewan, BC, about 2019. The upward trend of positive lightning is over a vast area. We feel it's not due to better sensor technology. We feel this is a real effect happening, and it may be due to ingestion of wildfire smoke. So I summarized those three things. Rocky Mountain barrier wave contributing to the downtrend east of the Rockies, uptrend in the north due to reorganization of the summer polar bear cleaning zone, then the uptrend in positive lightning due to ingestion of wildfire smoke and convection cells. And that's it. Thank you very much. That's the end of the talk.
Hello? I can see my presentation, but I don't hear anything.
Can you hear us now?
Yeah, I hear it right now, but I can share my screen. I think it's going to be easier if I speak and present at the same time, right?
We can try.
Yeah, I can try it. Let me try it right now.
So just while Wei Guang is trying to share his screen here, his presentation will be on operational implementation and update of the nowcast of weather element on the. Are you able to share your screen?
Let me try it.
No, we don't. I think in the interest of time, we're just going to use the presentation on this side, okay?
Okay, no problem. Yeah.
All right, so go ahead and,
Thank you.
start with.
Okay, thank you. So I'm going to present the nowcast system of weather element on grid that was implemented in CMC last year. For this year, we did a major improvement. So in last year's CMOS, Louis Plin already presented this system. And today I present some update of this system and some positive impact from the improvement. So next slide, please. Here is the introduction of this nowcast of weather element on grid in the big picture of ECCC. ECCC has a big system of numerical models and data simulation systems, and then the raw model output will go to a post-processing process for the weather element on grid. There will be statistical correction and more variables. So our system, the nowcast of weather element on grid, is after all those process. It tries to combines the model output with the most recent observations. Like I showed on the left-hand side is the surface stations, radar, satellite, lightning, and By combining all those most recent observations, we try to have a frequent update of this weather element on grid. The frequent update means that it could be 10 minutes, it could be 1 hour update. And the most important contribution of this system is to include the most recent observation and also early product, and also the frequent update. Next slide, please. So here is the simple schedule as compared to the other systems. In red is the nowcast system. So compared to the other systems which have extended forecast period, the nowcast has a forecast for only 6 hours, and it also includes a meso analysis at 0 hour. So what we try to do is to provide the impact of the recent observation on the first 6 hours of our forecast. Next slide, please. Here is a summary of our nowcast system. As I said, it produces a nowcast from 0 to 6 hours. As well as an early analysis, and it's working on the 2.5 resolution, covering Canada. The variables are the same as the HRDPS weather element on grid variables, and we support the projects like CAC and WINS. The CAC is the current atmospheric condition, and WINS is the system that we use to that the forecasters will be using to do the forecast. Here are some images about the basic variables such as temperature, wind, humidity, and you can also see some images about satellite, radar, and we produce some precipitation according to those variables. Next slide. Since I mentioned that it's a high frequent system, I'm just showing the frequency of the products in the system. The first one is the 2D surface meso analysis. The meso analysis are produced every hour, as shown here, and it has a delay of 15 minutes because we need to wait for the surface observation to come in, and then we do the data assimilation at a 2D surface level. And the second line is the blue boxes. They are the satellite observation, radar, and lighting observations. They come like very frequently. Some of them come every 6 minutes, such as radars. Some of them comes like a little late, but the frequency is about 10 minutes for the satellite data. The lightning, there is no latency. So we try to combine those data, and then we produce a new variable, which is called PCPO, which is the precipitation occurrence. That variable has a delay of 20 minutes. The delay is mainly caused by the delay of the satellite. So after we produce this PCPO analysis, we produce the extrapolation of the PCPO for the next 6 hours. We can see that the PCPO is produced every 10 minutes and has a delay of 20 minutes. So our main client is the like the high impact weather. It's going to be useful for them to make decisions based on the product. And the next product is the nowcast, which is in the green box. So we use the meso analysis and also PCPO to produce the nowcast, and we blend back to the model data after 6 hours. Next slide, please. So here I'm going to show you the blue box, which is the 10 minutes interval PCPO. So this PCPO use the radar data, satellite data, lightning, and convective cloud mask, which is also from, I think it's from the the L1 satellite observation. So the next slide. This slide shows the PCPO, which is the precipitation occurrence that we produced every 10 minutes. In here, you can see that this PCPO variable is a general image about what's happening in terms of cloud and precip. The gray means it's cloud, and the rain is green. You have intensive precip to the south. You have some snow and mixed precip to the north. And on the left-hand side is the precip. On the right-hand side is the nowcast. We use and the reason why we want to use a single variable like PCPO instead of different variables like cloud, precip is because when we do the pi step, it's going to be easier. We will shift the entire pixel to the new time step. So yeah, next slide. And here's the green part. The green nowcast is produced every hour. So it's just showing that we blend back to the model data after 6 hours. And the next slide. Here is the first installation and its challenges. So after the first installation, we saw some problems. The first problem is that we are using only the L1 data, and then the cloud field is not that good from our L1 our cloud fraction observation. For example, on the right-hand side, we can see that the cloud, which is gray, is not covering the precipitation. The precipitation is actually from radar, so they are processed separately. So from the radar, we see there's some precip, but the cloud shows there's no precip. And then because of this mismatch, the product is not really good. And on the left-hand side shows that when we process wind gust and wind speed separately, you can see that here's the histogram of the wind gusts of the wind gust minus wind speed. For many cases, the wind gust is smaller than the wind, which is not what we want. And the reason is because we processed those two variables separately. So we need to add more consistency check afterward. Next slide, please. So here I'm showing the second version, which was implemented a few weeks ago in CMC, and I'm showing some improvement. Next slide, please. The first improvement is just that we correct the wind gust. So all the wind gust that is smaller than the wind speed has been corrected. And at the same time, we also correct like some TT, like the dew point should be smaller than TT or things like that. So we do more coherence check. Next slide. We also include the satellite L2 data for the cloud. So now we don't use our derived L1 data, we use the L2. You can focus on the bottom two images. On the left-hand bottom is the binary cloud mask from the L2. And on the right-hand side, what we did is that we do a smoothing to this binary mask, and then we use this one as our new cloud. So the next slide. This one is showing the improved cloud field, which is on the right-hand side. You see that the cloud is able to cover the precipitation. But at the same time, it may create some false alarm because the cloud field is broader. So the next slide. Okay, the next slide is the third improvement we have done. We have the nighttime convective cloud mask, which is derived from the L1 data. But during the nighttime, there's no daylight channels. So the nighttime cloud mask is not really good. You can see on the right bottom, the figure shows a lot of noise, which is not consistent with our radar and lightning observation on the right top. So after our improvement, you get the left-hand side image. You can see that it's cleaner and the result is better. The next slide. So our current and future development will include like we want to use model data and NWC stuff to improve the cloud. That's for sure. And we also want to adjust radar because sometimes the radar beam is too high and the light snow cannot be seen, or in the summer the environment is too dry, so even the radar sees a little bit of drizzle, it will evaporate afterward. And we also want to include more observations from the surface. We can adjust the precipitation probability to avoid 0 and 1 and to be consistent with the surface observation. And we want to use the machine learning in our system as well. That's the end of the presentation. Thank you.
Thank you very much. We have time for a couple of questions. If there are any from the audience, are there any online? No questions online. I guess I have one, Wei Guang. You mentioned issues around data latency. Are there any prospective improvements in that issue in the future, or is that just something which is an irreducible challenge for this kind of work?
Do you hear me?
Yep.
Okay, so the latency is mainly caused by the satellite L2 data, and the satellite L2 data is from the US. So there's not much we can do to improve that kind of latency. But if we consider, if we trust our PyStep for the extrapolation, maybe we can use some old data with extrapolation to replacing our current satellite image, which will make the latency a little shorter. I think that's the only solution we can have right now.
Great, thank you very much. And let's thank our speaker once again before we move on to our next talk.
Thank you.
It's our next presentation is from Parvin Ghaffarian. Please come on up.
How can I change the slides?
You have the,
Which one?
should be.
Okay. Thank you. Hello, everyone. My name is Parvin. I'm research associate at UMBC. I'm going to talk about optimizing the weather research and forecasting model in a region of a steep slope Quinnell Lake Basin in British Columbia. The weather research and forecasting model, WRF, is widely used for weather forecasting and atmospheric research, and also in some countries, this model used for operational aspects and modeling in the mountainous region like Quinnell Lake Basin is challenging due to a steep slope. And this study explores how to improve WRF performance in such complex topography. The objective of this research is to investigate local wind behavior in the Quinnell Lake Basin to generate high-resolution atmospheric input for lake hydraulics modeling, to develop a high-resolution meteorological data archive for future studies, and to evaluate the sensitivity of WRF model to different physical schemes over steep slopes. In this picture, you can see the Quinnell Lake Basin. This image shows the slope of this area. As you can see in a green shade shows the flat area, and the brown shows the very steep slope area. In some areas, the slope exceeds more than 80% degree. And the Quinnell Lake is a fjord lake or glacier lake, and the maximum depth is more than 500 meters. It claims to be the deepest fjord lake in the world and deepest lake in British Columbia, and the third deepest lake in North America. We use the WRF model version 4.5.2. We define 4 domains, 9 kilometers up to 3,100 333 meter, and time step is very important. As you can see here, for domain number 1, we use time step 9 seconds, is a very small amount for time step, and the reasons is the steep slope area input instability in the model, and I have extensive experience using WRF model in mountainous area, for example, Alborz mountain and Zagros mountain in Iran, Anatolian mountain in Turkey, and Caucasus mountain in between Armenia and Georgia. And I have published many articles about mountainous area, but the Kunal Lake Basin is so special, and in my opinion, is unique in the world, because there are a lot of tall cliff. The height of a cliff reaches to more than 2,000 meters, and it input the instability in the model. And we use grid nesting, two-way and one-way nesting. The initial condition was 0.5, and we test some planetary boundary layer scheme, for example, MYJ and YSU, and long wave radiation, RRTM and RRTMG. And also, we should change the WRF model dynamics. First, we put the W damping. It's related to the instability due to a strong updraft, because in this area we have very strong updraft, and it insert instability in the model, CFL instability. And also we use EPSSM model, EPSSM value. EPSSM is the timing of centering. We use this value when we have the CFL error at the beginning of the run of the model. Due to complex topography, the value should set between 0.1 up to 0.5. The higher value than 0.5 inserted in error in the model outputs. And we use different terrestrial data. For example, in the left panel, you can see USGS, and in the right, Modis Lake. USGS couldn't successful to capture the lake, but Modis Lake, you can see the lake with Modis Lake in the right side. And also, we use the shuttle radar topography mission, SRTM, 3 meters. And in this 3D image, you can see the high cliff around the surrounded by the lake, surrounded by the high cliffs. And this area is it has a very complex topography, and working in this area is challenging. And also, when we use the SRTM data, we set the time step about 3 seconds, and it takes a lot of time to run the model. And we have a different automatic weather station around the Queen Lake, but we should consider the wind at the height at 10 meters. The stations was positioned in the less than 10 meters. We use the logarithmic equation to convert the wind to 10 meters, but we should have the accurate amount of roughness length, Z0, for achieving the exact value of the roughness length. We consider the shape of the land that stations located here, and also we use 3 meter DEM data and use GIS for determining the accurate value of roughness length. And we tested different physical schemes, And as you can see and we consider wind speed, wind direction, temperature, and relative humidity. As you can see here, in some stations, the wind overestimated, and in other stations, the wind underestimated, and also temperature, but relative humidity in all of the station is underestimated. Overall, the wind speed is overestimated, and the best configuration for simulating the wind field was MYJ or RTMG for wind and relative humidity, and for temperature, the best configuration was YSU and RRTM. And here you can see the wind rows. The top rows shows for dot point, observation, and different configuration, and the middle one, plateau point and goose point stations. As you can see in the dot point, the wind direction is consistent with observation, but in the goose point is very significantly different. Wind field direction is so complex because it depends on geographical location, interaction between land and lake, and also the roughness length and some obstacles, for example, trees and another obstacles. It's not easy to determining the accurate wind direction. And here you can see the histogram of the wind speed. And here you can see the wind field over Quinnell Lake at November 2018. And another achievement of this research is providing the atlas and also providing the data archive. In this picture, you can see the mean wind field for December 2023, for January 2024, and February 2024. And in the bottom, I zoomed the picture in the area near the center of the lake. I can conclude that the results simulating atmospheric parameters near the surface in environments with complex topography and steep slopes presents challenges such as model instability and slow run speed, accurately determining the roughness length for a station influenced by Earth interaction require high precision. The simulation results indicate that the model is highly sensitive to choice of surface boundary layer and long wave radiation scheme when estimating atmospheric parameters. And the key finding is the best wind and relative humidity estimation achieved using MYJ or RTMG configuration. We have a lot of error in relative humidity because relative humidity is not independent parameter. It depends on temperature, humidity, atmospheric pressure, and we should improve the accuracy of the model and use another parameters related to humidity. And best temperature simulation achieved using YSU or RTM configuration. And I want to thank from the BCS RIF that supported our project, and also DFO, and also from the University of Northern British Columbia, because they give me to access to Kilinaklinis cluster. And I took this picture last month from the Quinnell Lake. Thank you for your attention.
Thank you very much. And we do have time for questions.
Sorry if I missed it, but what was your input for your initial boundaries?
Boundaries?
Yeah, your initial input. Like what was your
Era 5. Era 5, yes.
I was wondering why you need to choose that particular rather than the most popular one in convection is more thermodynamic. The convection scheme we use, which is not the most popular one. So have you tried other convection scheme?
Because the convective scheme doesn't work in a very high resolution simulation. My resolution, my final domain resolution was 300 meters, and the convection scheme doesn't work for a domain less than 1 kilometer.
Hi, thank you so much. I was just curious, how long did you run the model for altogether? Because that's like a very high time resolution.
Yes, it's a very great question because it was my big challenge. The time is very important for me. I was too sure my configuration is the best. I removed my domain over the Pacific Ocean, and with this configuration, the model ran very fast. But then I remove it in the Kuna Lake area. It runs very slowly. For example, for 1 day, it takes 2 days. Yes.
And we have one online question.
Somebody asked, in your experience, how does the application of WFT influence the accuracy or quality of wind simulation in numerical weather?
Exactly. This is important because when we use the W damping in the dynamic of the model, it has not effect on the horizontal wind speed, but if I want to simulate the vertical motion, for example, the land-sea breeze phenomena, maybe it insert some error to determining the exact value of vertical wind profile.
So thank you very much. And I think let's give our speaker one last round of applause.
Thank you so much.
And we're going to move now to the last presentation of our session. Mustafa Kamal, who's going to speak to us about severe hailstorms. So, go ahead.
Hi, everyone. I know that this is the last talk before the lunch. You're all waiting for it. Okay, so before I start, I wanted to ask, how many of you are from Alberta? Okay, then definitely you will enjoy my talk. So today, when I was entering this room and I was looking at the weather forecast, and there is a thunderstorm advisory at Alberta, and it says that large hail downpour. So this is what I will be talking today. Okay, so again, I was born and raised in Bangladesh, but I came to Canada. And fortunately, there is a coincidence. I would say I studied severe thunderstorms over the Canadian prairies. And again, Bangladesh is one of the thunderstorm hottest spot in the world. And so this is why, okay, I decided to check, okay, is there any similarity, or I can take anything from here in Canada and implement in Bangladesh. So unfortunately, in Bangladesh, there is no hail, severe hail studies. Again, I think we receive more hail, but not severe. But so this is a good opportunity to learn from here in Canadian prairies and then implement it in Bangladesh. So now here you can see that, okay, the Canadian prairies, and then here, and if you don't know where is Bangladesh, it is sandwiched between India and the neighboring Myanmar. And so here I can show you the two pictures. Okay, although there are two, my study domain is from two different climatic regimes. We know that Canadian prairies in the mid-latitude and Bangladesh is a tropical country. However, you can see this picture. There is a good resemblance between the hail we receive in here, Saskatchewan, and the same hail over Bangladesh. So you can see the site is nearly a good match here. And If you don't know, I wanted to give you one information here. The world heaviest hailstorm fall over Bangladesh in 1986, which is weight 2.25 pound. You can imagine. Okay, so here again, I said there is a good similarity between Bangladesh here. Both countries get severe hail. However, there is a contrast between these two countries here. And again, I say another thing is that Canadian prairies, on average, receive 130 severe hail. And according to Environment and Climate Change Canada, which defines severe hail with 2.5 centimeter greater. And so another thing here, and you know that you may have seen this picture in Calgary. There is a hail suppression, and so the Canada is one of the richest country, and it has the technology and it have the money. However, in contrast, Bangladesh is one of the developing countries which does not have those money and the technology, and like. So this is the contrast. However, there is a similarity that in Canadian prairies, the agriculture, economy dominated by the agriculture, and the same thing in Bangladesh, the agriculture contribute the largest percent in this economy, and 46% of the labor forces are employed in agricultural sector. So now. Here, there is and the contrast in Bangladesh, in Canada, we know that we have the property insurance and the crop insurance. However, there is no such thing in Bangladesh, neither crop insurance nor the property. And now you understand, you can see one of the picture here, the most of the houses in Bangladesh are made of corrugated steel, and when this hail fall and it completely just go inside the houses. And you can see here the crop damage here, and this hail damage happened only just 1 week ago. Now here, another thing difference here in Canada, we know that we have a thunderstorm outlooks in day 1 and day 2. However, in Bangladesh, unfortunately, there is no thunderstorm issued by the Bangladesh Meteorological Department. So my research objective in this year, okay, as I mentioned at the beginning, it is the first study which is looking at the hail climatology, severe hail climatology over the Bangladesh and comparing with the in Canadian prairies. And at the end, I'll try to produce a climatology of the hail, so that actually the operational weather forecaster can use this information to advance warning of the severe hail event. So the data and method I use, okay, this is, I mostly use crowdsourced data. So here in Canadian prairies, I use data here from storm chaser, and all the case study I consider here at least greater than 50 millimeter. So just it is the extreme hail event. This is I decided to study, and at the same time I use ERA5. And so this is the, I think, 10 case study from Bangladesh and 15 from the Canadian prairies. And here you can see that, okay, the spatial distribution of the severe hail event over the in the right panel, it is Bangladesh, and you see, and that here in Saskatchewan and Alberta, all the cases here. And here, when I look at again, I say sounding drive parameter, and I look at it specifically that storm relative helicity, dynamical variables and also the thermodynamic variables. And I find that here that dynamical variables are play more crucial role in producing hail, specifically like a storm relative helicity, and also it is the bottom 3 kilometer storm relative helicity that makes a significant difference to this super hailer event. And again, I say now, then I compared the thermodynamic profile of the two hail event I mentioned here in these two. And here you can see that, okay, the first here in the left side, it is from the ERA5 and from the Canadian prairies, and the other side it's from Bangladesh. And you can see here that the big, large curvature of the photograph, and as you know that it is this strong relative velocity. That means that the rotating convection, and that brings all the moisture transported to the upper layer, and which is get more residence time of the supercooled water, and which makes this large hail. So here you can see that this the cape. The profile you can see here in left side in Canadian prairies. The cape, it is a little thin compared to the here in Bangladesh, where you see I mentioned that it is a tropical climate, and more moisture. Bangladesh is next to the Bay of Bengal, which is one of the shallowest ocean, where the warm moisture during daytime transport to the land, and which is making this moist profile and more cape. However, here at the same time here, this is there is a good question here. Like in Bangladesh, where I think the more abundant moisture, however, the less vertical wind shear. Compared to here in Canadian prairies, here we know that it's a very arid climate. Here, less moisture, however, more strong wind shear. And this is where it comes into play, that although two different climatic regimes, but this is the balance between the moisture, moisture and the shear, which is ultimately producing this hail event. And now here, that's again the composite vertical profile. It is the same. I mentioned this two picture, and you can see that here the curvature in the photograph. You see that the long, specifically the bottom, from the surface to 3 kilometer. You see the length of the photograph. It is really large, and this is which makes specifically this super hail, that this extreme hail event, and the larger the length of the photograph, and the more the bigger the hail. And when we look at it, the larger scale environmental condition, and we see that here that in Canada, Canadian prairies, it is the mid-latitude jet streams, and which is you can see here here the curvature here, you see that a positive vorticity anomaly and a positive curvature here, and the same thing here in Bangladesh. Here you see that however, the magnitude in over the Canadian prairies is high, and compared to the Bangladesh. But again, I mentioned here the Rockies, in Canadian prairies here in the east side of the Rockies, and where we know that Lee cyclogenesis happen here, and which makes more this, because of the conservation of vorticity here, we see more spinning up of this air parcel compared to here in Bangladesh. And so this is a radar reflectivity map, and you can see here, like I particularly mentioned, this is the main, I will show you later on again. Probably in the beginning, you may have, if you see that the most of the extreme hail event is on the northern and eastern part of Bangladesh, compared to there is not a single extreme hail event here in this part, western side. And however, because here, this is what happened here. This is the Meghalaya plateau. You may have, that okay, this is and this is the place exactly we call the Cherrapunji, which is where the maximum number of the maximum amount of rainfall in all over the world, more than 15,000 millimeter per year. And the same thing in the downstream here. This is the wetland, and it is a permanent wetland here. So, and the same where you see that, okay, and this is a Himalayan foothill. So when here it comes, and then just similar, you can consider here, and then this is the a Brahmaputra River, one of the largest river in the world. And when this moisture is coming, similar to the Pacific Ocean, you see that here, and then it jumps over the Meghalaya plateau, and then again because of the there is hydraulic jumps, and later on again I say here, and this moisture indicated moisture flux convergence here happen from this site, and which is making an ideal place for this abundant supply of moisture, and also that this going specifically the high orography, and which is making the lifting condensation level up, and this is Again, I said this is one of the key in dynamic mechanism that is acting as a mechanism for this superhalo event here, specifically in all the northeastern part here. And so here, the key take home message here, we find again, I say, although the two different climatic regimes, in mid-latitude here in Canada and compared in tropics. However, we see that here that both in all cases here, in both in Canadian prairies and Bangladesh, the both large-scale environmental conditions, here again, I think Canada mid-latitude jet streams, and compared to in Bangladesh where the subtropical jet streams and as well as the western disturbances. And I know that I think probably many of you are here about western disturbance, which originate from the Mediterranean Sea. And the other thing is here common, which is again, I say orography here in the Rocky Mountain, and in Bangladesh, it is Macallan Plateau, and here. And here, again, I mentioned that, okay, the dynamical balance between the shear and the moisture instability, which is balancing into condition and then producing this superhalo event. Thank you very much for your attention. I'll be happy to take any questions.
Thank you very much. We do have time for one question.
Yes, please.
Yes, in Bangladesh, what is the height of the elevation of where the hail usually strikes?
The Macallan Plateau, 1.5 kilometers.
1.5 kilometers above sea level?
Could you repeat the question and the answer for the? Could you repeat the question and the answer for the?
Oh yeah. So I think the height of the Macallan Plateau is 1.5 kilometers above sea level.
And I think that actually brings us to the end of today's session. So let's thank our speaker once again. And I'd like just to thank all of our speakers in this morning's session and remind you that we will reconvene at 1:30 this afternoon for the second part of atmosphere, ocean, and climate dynamics. So enjoy your lunch and see you this afternoon.
I'm learning to do the work now, so I really want to.
Thanks a lot. It's a trial by fire. No. We're all learning. We're all learning. So it's Are you this afternoon? Okay. Thanks. All right. Thanks again. Do we keep this all going or do we log out? I think we have all the talks for this afternoon. I just want to confirm here. Yeah, we have 4 talks. That's good. So I'm not sure what happened this morning.
I like it better. That's Farsi, right?
I should stop sharing.
Okay. All right. Thank you very much.
Thank you.
I did some field work, so that's kind of what it's about. I'm using water now.